Welcome to this demonstration on analyzing the weld frame in the ASCA welding fixture. We will be testing the structure for performance, simulating the load coming from the robot arm. The concern is whether or not the frame will provide adequate support. We also want to ensure there is not too much movement or vibration as the weld is applied to the automotive components in the fixture below. Let's begin. There are multiple approaches to set up the study which will provide various types of results to gain the information we are looking for. Are we concerned with stress, displacement, axial forces, bending? All of these questions will be answered in a matter of minutes. Solid elements is a traditional approach to meshing the model. However, here we will use shell and beam elements to gain results faster and even provide information that solids are incapable of. As you can see, the mid-surfaces are detected and the thickness of each part is automatically applied. Let's go ahead and create the mesh. Each of the components are shown with different colors and can be changed, making it easier to distinguish between them. Next, we will add boundary conditions to describe the behavior of the environment. It is held down to the floor at the bottom, and there is also a load that is applied from the robot assembly. In this first study, we will assume the robot is not moving. Stay tuned for dynamic loading conditions in just a minute. Contact conditions can also be created for all the components. Here we are ensuring there is a welded bond in cases where there is a possible gap between mid-surfaces. The solver runs very quickly for shell elements as there are fewer nodes to calculate compared to solid elements. This just takes a few seconds. There are several result plots available for shell elements such as principal stresses, maximum shear, and bending to name a few. And they offer an option to see the stress on the inside or outside of the tube without having to section the model or hide components. Now let's have a look at beam elements. The physical properties of each component contain several predefined options for the shape and cross-sectional size. Here we have a square tube at 100 mm with a 5 mm wall thickness. Once again, we will hold down the bottom of the weld frame where it is fastened to the floor and apply the same static load you saw in the previous study. The process for meshing and solving the beam elements is almost instantaneous. This allows us to run several what-if scenarios in a short amount of time. Now we have other types of plots available, such as axial forces on each of the steel tubes. The bending moment can be plotted as beam diagrams in the Y and Z direction. Then there is also maximum and minimum values for stress under tension and compression. It looks like the highest stress is near the upper portion of the frame, and it doesn't seem to be a concern. However, displacement may be a concern with the welding process. And it is important that we consider the motion of the robot arm. Let's begin by copying the current study and change it to a normal modes type. Here we are looking for the natural frequencies of the weldment without the applied load. This again meshes and solves very quickly. Taking a look at the result plots, we will start by looking at the first mode shape at about 43 Hz. Animations also aid in observing the behavior of the model. We can see that the least amount of stiffness is in the Y direction. Let's take a look at the next mode shape. It looks like this one resonates at almost the same frequency, and it is a bigger concern due to the motion of the robot arm. Let's take this a step further using a dynamic load. Once again, we will make a copy of the previous beam element study and change it to direct transient response. Now when we edit the load, there is an option to add a timetable, or define the dynamic behavior of the load. We will apply the 2000 Newton load over a fraction of a second and let the robot rest. There are additional settings for the amount of data we want to collect over time. In this case, we will take the results over 100 time steps, which is adequate. The more the better, keeping in mind solve times and file size. Also, we don't want to forget damping. There are options for structural, Rayleigh, and modal damping methods. Now we have the ability to see the results over time instead of a steady state. We can see in the graph the frame oscillates at a nominal distance after the robot moves. We may be able to save money on material costs by going with a smaller tube size. Since we are in the CAD environment, we can make the change to the 3D model, or in this case we can simply change the cross-sectional properties for the beam element. After running the solver, we can see the deflection has slightly increased and oscillates more, but our design requirements are still satisfied. As you have seen in this demonstration, Autodesk takes us beyond linear static studies and utilization of shell and beam elements to gain a full understanding of our design. Run quick what-if scenarios to ensure the structure is sound but not overbuilt. Autodesk is your trusted solution for virtual testing. It is the future of making things.